Hi guys. So we have come to decision tree. So we started with introduction to AI, intro to machine learning, linear regression, logistic regression, and we started with decision trees yesterday. And uh, Matter of fact, it is actually yesterday I didn't make a video. Um, I mean, I was actually more studying without making the video. The video, actually, it's supposed to be study time where I'm supposed to set up the video, screen share, and then keep studying. But what I'm doing is actually I'm setting up the video. I'm just talking. I'm not studying real study, right? So I'm more on uh, providing information or giving out what details what that I like to provide. So what I'm focusing on is yesterday it was more on understanding things because um, I myself had a lot of questions. I thought like I started off yesterday saying I'll clarify all the questions and then I'll get into um, uh, I'll get into video, but uh, there are a few things that I didn't understand, and once there are things that I didn't understand, I am behind it to see how it is done and stuff. Okay. That being said, let's get back to decision trees, right? So I told you guys when we were studying linear regression and stuff, most of the algorithms that at least what I have seen, they are one version, another version of linear regression is what I see. So, same here. Decision trees also for you guys. If you clearly understood linear regression, I'm just quickly recapping it. So, if you take a plane and if there are multiple points in the plane, which are actually features, and all of those features combined together, they try to predict a y, right? So it's like this, and then you have a lot of points. These points are nothing but x1, x2, x3, x4, whatever. So, and those all try to predict y, correct? So that's linear regression, right? So mm, here in decision trees, what this guy is really doing is, see, when you draw y is equal to w1 x1 plus w2 x2 plus w3 x3 plus b or something like that, it's it's not really a straight line because obviously, right, it has multiple features unless you put it on. Mm, because if it is y is equal to wx plus b, it makes sense, it is one feature. But whereas considering x1 x2 on two planes and y, then it can't be a straight line, right? It will be a three dimensional. So you can't draw a line in three dimension. Three dimension should be a plane, right? So what happens here? Yeah, but that's complicated to imagine, but that's how it really works. So we in all the tutorials or our learnings, what people do is, yeah, just let's just talk of w1 x1 plus b and then try to explain it. But the real use case on the ground is never like that, right? There's never one feature and predicting why, because if there is one feature, there are a lot of ways we can predict it. Instead of using all these algorithms and stuff, you can directly predict what y is close by, at least maybe not be that accurate, but the challenges we are talking about real world, the features could be many. There are features that are hundreds of features also is possible, um, and still we need to deal with things. Okay, now getting into um, decision tree, right? uh, Using decision trees can be used for both. It can be used as um, it can be used as classification algorithm and also regression algorithm. Okay, that's good. How do you do classification with decision tree? Correct. Let's start with that. What decision tree does is, there are multiple features. Instead of taking a complex linear equation, and where we don't know what degree of polynomial it could be, what combinations we should pick up, and all that, instead of making it complicated. The more it is complicated, the more it is complicated with respect to computing it, with respect to deriving that equation, and all that, right? And another underlying assumption is that all these features influence y directly at a given point of time. But the reality would be, if there are 100 features and your y specific thing, we very much know that there are certain features which influence y majorly, and then the other features which influence low. So the how is it determined? That is determined by W1, right? So if something is influencing more and something influencing low, what we will do to reduce the impact of that particular feature on y, we reduce the weight. Like something which is made 0.001 into that particular feature, assuming the feature is somewhere in hundreds or something like that, once you multiply with 0.001, it becomes very small, right? Whereas another feature which is very important, which is actually is directly correlated to y very closely, then what we do, we increase w, like we make w 100, right? Assuming x2 is in some 20s, 30, something like that. So what happens when you 100 into 20, it becomes 2000. So the other weight you're multiplying with 0.001, and this weight you're multiplying with 200. So mm, the basing the just by adjusting weights, we by adjusting weights, we are actually deriving the impact, like we are predicting y, correct? But what happens, we are picking up all features in one go, and then we are trying to predict it, which is where, even though you start with one single, I mean, as we discussed, we will pick up random w1, w2, w3, w4, right? Let's assume that usual practice is we pick up the same number for all of them, maybe w1, w2, 0, 0, something like that. So that's also a good discussion on how to pick up what is the W1, W2, how to pick up learning rate. These are all good things that needs to be learned. I didn't cover them in detail in this, but those are the practical things you learn when you really try to solve an problem statement using the algorithms. Because uh, these when you study, right, all you need to know is what is linear regression, how w1x wx plus b is calculated, how loss function is calculated, how cost function is calculated, how gradient descent happens. That's all. But the actual decision making happens in the real world, right, where you actually try to solve a problem. Then you'll actually face similar questions. Is like, okay, all this is good, but how do I determine what is my first w1 w weights? Okay, how do I pick up a good learning rate, right? um, how do I make sure that I'm not stuck in local optimal solutions, right? So there are a lot of things, and how can I fine tune um, my data? How can I fine tune my data in a ways that the calculation gets easier? There are a lot of things practically that gets into picture, because these challenges online, they'll also to push you towards a specific solution, or to push you to make an efficient solution. They'll restrict on what kind of how much time you can run the algorithm for a given data, and how much compute you can use, and I think that's the thing. Restricting on libraries is very rare, but yeah, that should be fine. As long as you have one good library, it will cover all basic required details and all that stuff, right? So, and, okay, that's actually important. That's actually a practical error. Now, coming back to decision trees, why I'm explaining all that is, um, to re- to simplify the whole thing, right? People say, okay, let's simplify. Then they thought, like, let's say, instead of considering all features at a time, how about I go with simple one feature at a time. Okay, and then one thing. Second thing, I want to go with um, I want to go with linear regression, but I want to go with something which is simple, like um, just x is equal to a kind of aligns. And when I say x equal to a, yeah, x is equal to a, consider x is equal to a, but the the decision tree is, as it's a decision tree, it happens to be like x greater than a kind of stuff, right? But actual equation that you draw there is x is equal to a. You draw a, and then you classify things on left and right side, and so that's an easier linear equation, right? So it becomes x y is equal to uh, oh, interesting. If I say x is equal to a, that's a different subject. But if it, so what I'm trying to say is x greater than a. Okay, so because what happens is when x is greater than a, you split that particular data set that is there. You take a line, you say x greater than a. So what happens? X greater than a covers, makes always into two parts, right? Whatever data set you have. But the two sides of it may or may not have, because depending on a, right? Because let's say there are these all points and then x is a at the end of it, then there is only, let's assume there is only one point on the left side, or there is no points on the left side. So you have all the points on one side. That's also possible. So the x is equal to a, when you have a graph like this with all the points, x is equal to a can be anywhere on the x-axis, correct? Considering that case, the the point segregation is different. So that's we'll get to that. Like, how do you pick that a, right? That's the important thing. When I say x, it could be any of the features, but preferably they pick one feature, x1, x2, x3, whatever. So what they do, they pick up one single line, and basing on that line, they classify the data. Um, they split the data basing on that particular equation. They split the data, and then see how efficient is that split. And ba- so how efficient? When I say how efficient is, how closer does it take us towards our derivation? For example, we are discussing about the decision tree with classification, correct? So, what's our objective? Our objective is to classify given set of data. We need to classify and say how many of them are. That's simpler is binary classification. How many of them are apples and oranges? Uh, Bigger example: how many of them are malignant or benign cancers? How many of them predict saying the machine has a problem, doesn't have a problem, like that? There could be a number of binary use cases. Then similarly, there could be multi-class classifications where maybe you say what is the probable color output, or what is the probable age group into this age group of the person for which the data is available. It could be multiple things into which multi-class classification can also work, right? So what happens, we take we start off with one single line. Okay, so on a given graph there are points all across. You draw one line. Okay, then what happens? The line, the points that are there in the graph, if I draw a line, there are points on the left side, there are points on the right side, correct? So it's more like a divide and conquer, right? So instead of drawing a line which is closer to all the points, which is difficult if they are widespread and stuff, right? In a linear regression, that's our major problem. That's where our loss is, right? So you try to fit in one single line or single curve that actually goes that predicts corresponding y for all x. And so what you can do, But let's think of you draw two lines, and two of them will cover some part of the points. Like for these points, this is the line, and that line gives me prediction. For these points, this is the line, and this gives me prediction. And then basing on the point where it is, I decide, I take whichever algorithm. So then what happens? If you imagine that concept, what happens? You start start dividing the whole prediction of given x, like the data sets and y, basing on the range of x values. You can divide them into multiple smaller chunks, and then you solve each of them separately. And all you need to do is once the incoming data comes, you should classify them and say, you should segregate, saying which bucket of x does it belong to. If it belongs to this x, then you put it there, and there you have a model specific to that x, and you solve that particular x alone, and then that gives you y. What happens? The range of x is limited. Obviously the y also, I'm assuming, could be narrowed than the broader scope of the complete data set. So you're breaking down to smaller data set, and you're trying to solve problem. Similarly, so, and you agree with the fact saying the more I segregate, the easier it is to classify and more accurate it is, because you have the whole data set of 1 million records, and you have one line trying to predict y for all of the 1 million records. Two, I break down the whole 1 million into 10,000 chunks, and in 10,000, um, if I um, if I try to predict for each 10,000 separately, then it's much easier, right? To classify. So classify or anything, but let's say talk of classification. So it's easier, definitely. So that's the whole approach of these decision trees and other algorithms that are there and stuff. So what happens in decision tree is, it tries to break down the whole point. So I start off with one single line, and from that line I break down the left and right. Okay, the first thing that we need to do is to pick up this line, like what is the right line to pick up, but we'll come to that later on. How do you make a choice on which line to pick up and stuff? Okay, that's one thing. Second thing is, once you break up, you get the points. What you do, you deal with them separately, because you know how to break them down, right? So you've broken them down. Now you, after breaking them down, now you have two different data sets in your hand, which you need to deal with, and you deal with them separately, right? Because you know that given a problem statement that comes in, you can actually take it to through to these two directions, where there is no overlap in between two of them. Agree? So you deal with this problem separately. Now again, if it is still, you think it is data set is huge and it has the mixed classification, you break it down. How much do you break it down is, you need to reach the leaf nodes. What does a leaf node mean? Like in a binary classification problem, you take mix of all apples and oranges on the top, you break it, you draw a line and say, this is the left side, this is the right side. You put left side and right side. Do you see left side and right side? What is a mix of it? Is it all apples? Is it all oranges? If any of the leaf node has all apples or oranges, that's the end node. You stop there, because your objective of classifying is reached. Now on the other side, if you have apples and oranges, you break it down again still. So how much do you break it down? How do you make a choice of the lines? How much do you break it down? How much do you break it down? Question is, um, you break it down until your leaf nodes has um, has only the single class items. That means only apples and only oranges should be there in the leaf nodes. Until that point, you keep breaking down the tree, like from top all apples oranges, break down maybe apples oranges on both sides also possible, yeah. And then you break down, try to achieve apples alone, oranges alone on one side, and then you keep breaking down until you get all apples and oranges kind of stuff. So now what has happened is, instead of um, instead of dealing with the whole data set, and instead of solving the problem from complete data set level, I've broken it down to smaller pieces, and now I'm solving small problems, and then small problems are easy to compute, faster to compute and stuff, and that makes it easy. Now again, So what I'm doing is I'm drawing lines to break it down, right? So this line is nothing but what? It's linear regression. Um, or logistic regression. If it's a classification problem, it's logistic regression, right? So I draw a line. Then I say, this is my algorithm. Okay. Let's imagine I'm at the root node, right? Top node of the decision tree. I draw one single line and I say, this is my logistic regression algorithm. What do we do? Straight line. Z is equal to Wx plus B. Um, then you calculate logistic regression 1 by 1 plus e minus z, the sigmoid function. And what happens to it? What is the loss function? Focus is to reduce the loss. That's all, right? So the objective of always or the is to reduce the loss so that the y and y predicted is close to each other. So how do you calculate loss? The one which we study. Let me share my screen. Stop showing my face. Share and then open the book. So how did we do log loss? Oh, okay. This excuse me. Sorry for that. So what I'm gonna do is I'll move forward with it, considering an assumption you guys understood the log loss and all that stuff. But I'm gonna make another video, which should be day 10. In day 10, I'll revisit logistic regression. I'll revisit decision trees, this overlapping concept of what is this loss function, log loss function, binary cross entropy, all these complex terms that are there. What do they mean and stuff? I'll get to the detail because that's what I've spent a lot of time yesterday, and I want to share with you guys also and what I was doing and all that stuff, right? So, uh, uh, coming back. So what I'll do for given xi is equal to one term, I can actually um, one second. Sorry, guys. Sorry. I'm just trying to see how could I tell you guys on how um, we are dealing with this clearly, right? So mm, if the if the all the points are taken and you calculate the loss function binary cross entropy, it will give you certain value. Now you segregate it into two pieces and you calculate the binary cross entropy, that is the loss function, um, uh, for each of those points, and then you see how much you've read. Yeah, fine. So you consider a data set where you have all the points available, and you predict logistic regression is nothing but you draw a line and then I'm just thinking, guys, give me a minute. You draw a line and then you map that particular line's points to a probabilities to say for each point on the line you try to map it to using a sigmoid function. You try to map it to a certain value, and that certain value is what we cast it as probability of that particular x1 x2 x3 values at that particular um, value. Using this algorithm will predict the probability of classifying that particular thing as x is equal to 0 or x is equal to 1 kind of stuff, right? That's what you calculate, and then your loss function shows whatever you try to predict for that particular point, how far is it, uh, how much difference is it having relative to the actual prediction, that is the actual classification. That means 1 minus the probability of predicting that it is 1. um, That's what we do, and then we calculate entropy. Entropy will tell us how far are you from the actual classification. Your algorithm says the classification is this, and then the actual classification is that. Correct. So if you start with um, if you probability of no, entropy loss is high, it should be so. i- Anyways, yeah. So you start off with you start off with having all the points available. Okay, so then you calculate uh, the entropy, right, for all the points. Then what happens if you have all the points? The probability of each point being predicted means you imagine you draw a line and all the points are on one side of it, right? So what happens then? All the points are available. That's also not the, yeah, you can consider like that also. But what happens, the entropy at that point of time is, you have every point that is there, and then you calculate the probability. The probability will become um, one point being, let's say it's apples and oranges. One fruit being uh, one fruit being an apple compared to all the fruits that are there, right? That's how the probability works. Um, that's how you predict the probability for all the um, apples, and then that's how you calculate the probability for all the oranges. One orange being valued being an orange compared to whole fruits that are there. So then it's more like you put everything into one bag and then you pick up. That's probability, right? Yeah. So starting off from there, you calculate the entropy of the overall or apples and oranges that are there in the bag. So what happens? Your probability or the overall entropy loss is calculated by minus 1 by n. I mean, I'm referring to this one, right? No, that is actually um, logarithm applied, but it's actually a binary class specific to binary classification. That's the reason it shows 1 minus y and 1 minus pi and stuff. That only two things. But whereas if you generalize it, it is you can write like, let's say the second one is pj, pi and I and j are two classifications. Then it will become yi log pi plus yj log pj. Correct. So basing on application, it will change. Um, um, oh, sorry, I'm very much distracted. I'm very sorry. The bad thing is I'm explaining things on air, and then I'm just trying to see how far you guys can understand. But let me step back on that. I should not be worried so much on making sure how far you're understood, because uh, I'm not putting things on somewhere. I'm just explaining in the air, so I can't help it. That's how it is. So let's move forward and see how do you calculate entropy and information gain and all those things. Before getting into those concepts, I'll actually want to show an example saying, given all these features, then what you do, you pick up some line like this, and then what happens, you once you draw a line, you can actually classify. Let's assume there are to understand uh, it much better, there are 10 apples and 10 oranges. This feature comes in, and then you have 4 apples on one side, and you have 16 fruits, and which are 10 oranges and 6 apples on one side, right? So initially the point is 10 apples, 10 oranges, right? So what happens, the probability of picking up an apple is 10 by 20. It is 0.5. The probability of picking up an orange is 10 by 20. Again, it is 0.5. So what happens, it is 0.5. If you put it into that formula, it will become 1 by 20 into 0.5 into log 0.5 multiplied by 20. So 20 is 0.5 log 5, log 0.5, log 0.5 to the base 2 will be approximately 2 to the power. How much is 0.5 is, um, if you look at it, let's look at this thing log. Okay, what is there, what's the big deal? Let's just pull up and calculate it instead of thinking so much, right? Okay, not this one, not, yeah. Also I don't need, I'll just say 0.5 into r. That's also not required. Just say log into log of log base 2 of 0.5 is, minus 1. Okay. Um, Assuming that 2, right? So yeah, so there are 2. Okay. What it will become is 0. I'll write the form. Sum of entropy is sum of uh, pi log pi. Pi into log pi. That's it. Okay. It will be a negative sum minus of sum of log pi into. So what happens here? I should put it in our document. These are few days where the disturbance is there, and then there are people pinging on different topics, and I'm just thinking about it. I'm sorry about it. It takes a lot of time for you guys because of that, but that's okay. Happens. So this is the formula, right? So let's start with root node. The root node, if you calculate this, it will become so minus 0.5 into log 0.5 for apples plus minus 0.5 into log 0.5. So this is equivalent to log 0.5 is minus 1, correct? Minus 1 into minus 0.5 is plus 0.5. It's 0.5 plus 0.5 is equal to 1. So root node, the entropy, the loss is calculated as 1. Okay, now coming down, let's take each of them separately. There is, if there are 4 apples, what is your log loss, right? The prediction with respect to oranges, if you look at it, it is 0, right? 0 by 4, 0. And so that calculation, okay, on the left node is equal to probability of apples is 1 into minus 1 into log 1. Yo, 0. Yeah, let's see. And not plus, minus. Here also it is minus only. Probability of apples is, of this set is 4 by 4. 1, correct. Probability of oranges is 0 by 4. 0. So it will become minus 0 into log 0. Log 0 is undefined. You can't, any power of 2 will not become 0, right? Undefined. But doesn't matter, the it's multiplied by 0, that is not considered. And log 1 is 0. So that is log 1 is 0. So 1 into 0 is 0. So again, the value, overall value is 0. Right node is equal to the probability of oranges is 10 by 16, correct? So let's use again this thing to calculate it. So 10 by 16 into 10 by 16, dude. I know 5 by 8, man. Okay, so fine. 0.84 8 5 is 40, 8 6 48, 6 0.6 2 5 0.625. So 0.625 into log 2 of 0.625 will be, oh, I said it's wrong. Actually, I could calculate the whole thing in one go instead of doing all this nonsense. This is 625 plus 0. So 10 by 16 is what we did here, and then now we can do 6 by 16 because remaining are 6 by 16. But other way, if you look at it, is 1 minus 0.625. That will become 375. 0.375 into log 2 of 0.375. Okay, you do whatever, man. Just give me answer. Yeah. Minus 1.03. 1.03 is what it's trying to say. It should not be the case because the entropy is supposed to come down, right? Yeah, there's something wrong with the chat GPT. Its calculation was not correct. Okay. It's 0.95. Okay, 0.95 because minus is there. I apply minus across 0.95. Where is this document? Yeah, right node is to get you guys one. I kept it for Apple, so let's keep apples on the first so that we are consistent. It's 4 by 6. It's 6 by, sorry, 6 by 16 into log 6 by 16 plus or minus here and here also minus 10 by 16 into log of 10 by 16 is equal to 0.94. Okay, 95. So this is what is your entropy that is there. But if you look at it, the objective, as I said, entropy is on the top is actually 1, right? And we brought it down to 0.95 here. After this, if you if you split it now, you have 0.95. Okay, that means to the loss of this particular thing is 0.95. Previously we had calculated saying everything is on one side and then the entropy loss is 1. Now it is 0.95, but you can't just add 0 plus 0.95 and then say it is 0.95. That's also not a right thing because um, it could be like the number of points on the left node are only 4 and the number of points on right side 16 points. So the loss of predicting values for 4 points and loss of predicting values for 16 could very much be different, right? So what we do is we um, add a weight to it so that it makes more sense, right? So anyways, this is entropy calculation, but entropy just tells us for each node what is the loss that entropy value that is there, which is in turn nothing but the overall log loss to represent what is the loss if you go with this kind of a classification, correct? We in order to take a decision on what is the right thing to classify, because this is 4 apples and 10 16, but let's say I have another option of splitting it, that is I have uh, let's say I have 5 apples and 3 oranges on left node, and I have uh, remaining, right, like 10 minus 5 apples and 7 oranges here. Now what happens to the math, right? So we again need to calculate for this is left node, this is right node. So for left node, what is the value, right? So it will be apples 5 by 8 into log 2 of 5 by 8 plus 3 by 8 into log 2 of 3 by 8, right? So this is something we need to calculate, and then right node will be node is equal to 5 by 12 into log of 5 by 12 plus 7 by 12 into log 2 of 7 by 12. So let's calculate. We should apply minus and interestingly, this is also is this correct then? The same value is coming again and again. Maybe it is correct. Let's look at it. 0.95. But the calculation, the way it's reading is correct. 5 by 12 plus log 2, 5 by 12, 7 by 12, log 2, 7 by 12. Okay. So this is 0.97. Now, if I sum it, I can actually clearly see it is not correct thing. Also, just left node plus right node. If I do also, it is the second classification is very high, whereas the first classification is lower, kind of stuff, which is okay. So, but also looking at our objective, the objective is to reach the leaf nodes on all trees, and the leaf nodes are nothing but the ones which has more single classification, right? So the first one has that. That's the reason I think that is having a higher value. But again, as I said, I can't add 0.95, 0.35. But example, let's say there is another use case where there is 3 apples and 4 oranges and 7 apples and 6 oranges, right? So and you can't add them directly because the number of here there are 4 apples, there are 16, 4, 16. Here it is 8, 12. So the distribution is also different. So to weigh in those distributions and then make the calculation much better, what they do, they calculate something called information gain, right? The term is, they call it information gain, IG, information gain. This is nothing but to see what is the overall entropy. They sum it with the weights. That means with their corresponding root node. For example, for this information gain for first division is equal to it is the two values, right? Left node and right node. This is left node. Left node is 4 apples, so it's 4 by 20 into 0 plus right node is 16, right? So it is 16 by 20 into 0.95. This is the information gain on the first one. The second one, information gain, is second division is equal to so this is 8 by 20 into 0 8 by 20 into 0.95 plus, and this is 12 by 20 into 0.97. So let's calculate this. This is 0 already, so all we need to calculate is only this. 0.76, and second division 0.962. 962. So now you see information gain ways. If you look at it, the weighted entropy, sum of weighted entropies is nothing but information gain. That's all. So because if you add it, if the numbers are bigger, the values are bigger and would be bigger, and you should not um, add them straight. So we go with weighted entropies, and weighted entropies clearly gives a decision saying the first classification is the better classification for decision trees, and we should go with that particular classification. Correct. So that's how you make a choice, and then we move further down on each part. So like again, 10 oranges and 6 apples. Again, you draw a line and then classify it, and maybe you get 5 oranges one side and 5 oranges and 6 apples on another side. Again, you pick up 5 oranges, 5 6 apples on one side. If you can draw a line assuming 6 apples on one side and 5 oranges on one side, you're good, right? You have all the leaf nodes which has only apples and oranges. Then a new use case comes in. You traverse through this particular decision tree saying basing on x1 is greater than 1, x2 is less than 3, something like that. You traverse that particular decision tree, and then you reach certain leaf node, and the leaf node gives you prediction saying for given these x features, x1, x2, x3, x4, the the classification says it's an apple, or the classification says it's an orange. So that's how the decision trees would work. I am assuming this is clear, and you also understood how it is coming. But I'll also quickly show you guys from visualization perspective, decision tree lines graph, and then show images. Come on, man. Yeah, something like this, right? So see what this guy did really is, he's classifying survived, and he's creating multiple decision boundaries. So he's given drawn this line first. Initially he has drawn this line, and then once he has drawn this line, he has left and right. And what happens if you look at it, you forget about this piece part of it. You take right one, then he has drawn another line like this within this, and he has classified this and these as two separate points. And coming to the left node, for all of it he has drawn this line, and then he has classified all of them as one set, and this is one set. This being majority of are blue, he left it like this as this one, and these he has drawn this line, and he classified them into two parts. All of this is into one part, all of this into one point. And again, for this he has further has classified by drawing lines into sub pieces, kind of. So most probably he has drawn this line first, and then he has got these points in one side and these all points in another side. Then he has drawn this line, and he got these points and all of these points. Then he has drawn this line, and he got these points and these points in between. So this is how he is drawn the lines, and he is splitting the whole problem, and he is solving one problem at a time. So that's how he's really done it. Okay, so I think it took a while is what I'm thinking, but let's go back and the presentation. I hope that is clear to you guys. See you guys in the next video.